Right, so we are going to look at local counter encryption. So in local counter encryption, so this continues from the previous example. So earlier we did global counter encryption. Now we are looking at local counter encryption. So we assume counter mode encryption using 2-bit local per basically local counter. Suppose that a seed is formed by concatenating the last 2 significant bits of an address with a counter value, and assume that a counter is incremented before being used for encryption. Again, this is standard in a class. Use block cipher encryption table from question 1. So I included right here. Now, and then the rest is block A with value of 1110. Located at 1000 is dirty, needs to be written back. Okay, let's first construct this. Value, address, and counter. So the value of block A is 1110, address 1000, and then the counter value is 00. Okay. Block B has a value of 1110, address 1. Okay. Here, right here, 1001. Corresponding local counter value of 00. Okay. Now, how is local counter encryption is performed? Well, if we remember that basically this is the cache, and this is block that we want to write back, and we form a seed, and the seed is basically, in this case, address concatenated with local counter. Okay, and this form the seed. We pass it through encryption block cipher. We get pad, and then these two will be XOR. This is a trust boundary right here. And then with this will be placed in memory. Okay. So the difference with a global counter encryption is here we are using a concatenation of address and counter. Now, typically we don't need any to trim any of the address or a counter in a real, memory encryption. But here, because we have a toy example with only 4 bits, so we have to trim something, right? So from the address, we will use 2 least significant bit concatenated with the counter. Okay, let's start with block A. So block A, so what is the seed? So seed will be concatenation of the address, which is 00, right? Right here, 00, concatenated with counter value. But remember, we increment the counter value, so this becomes 0, 1. All right, so this result in pad the pad is the encrypted version of the seed. So the seed is 0001. So we look up the table and we find 0001 right here. The output is 1000. So the pad is 1000. And therefore the ciphertext is pad XOR with the value of block A. In this case, the pad is 1000 XOR with the value of block A, which is 1110. And here we get 0110. Now let's look at for block B. Okay, I'm going to shift this a bit. Okay, block B. What is the seed for block B? This will be the least significant digits of the address, which is 0, 1. Concatenate with the counter value, which is 0, 0, but we increment it by 1. Therefore, it becomes 0, 1. So the pad is the encrypted of 0, 1, 0, 1. And if we look at the table, 0, 1, 0, 1 leads 1, 1, 1, 1. So then the pad is 1, 1, 1, 1. And the ciphertext is then pad XOR with value of B. This yields 1, 1, 1, 1 XOR with the value of B, 1, 1, 1, 0. This becomes 0, 0, 0, 1. Okay. There you go. So again, a little note. So even though block A and block B have the same values, but they have different address, and therefore the ciphertexts are different. Okay. Now the the counter also allows that every time the block is written back again from the cache, the counter will always be different each time. Therefore, the seed is never reused. All right, that's it.